Hello. In today's lecture, we will be discussing about the fluid in the cardiovascular fluid mechanics, which is blood. So, the topic for today is rheology of blood. So, let us look at the definition of this term rheology first. Rheology comes from two terms, rheo and logy. So, as you would have studied in a number of terms that logy or logos means study, and rheo means, it is a old Greek term and it means flow or stream or current. So, rheology etymologically or literally means study of flow or study of current. Okay. The term was coined by two rheologists, Professor Eugene C. Bingham and Professor Marcus Rheiner. These two are famous rheologists. If you have done a course on fluid mechanics, you might have had a subtopic on non-Newtonian fluids where you would have studied about Bingham plastic fluid. In this lecture also we will be studying what Bingham plastic fluids are, so that those Bingham plastic fluids are named after Professor Bingham. And Professor Marcus Rheiner, he has also given a number of rheological models for complex fluids. So, if you do a detailed course on rheology, or if you study in detail about rheology of non-Newtonian fluids, then you will come across about the work of Professor Marcus Rheiner. Okay. So, the rheology literally means the flow of study of flow. So, to understand rheology, when we apply a stress or a force on a fluid, what happens? The fluid starts continuously deforming. Unlike a solid, when we apply a force on a solid, then what happens? The solid deforms and then it stops after some time. Now, once the force has been removed from the solid, then the solid may retain its position completely or partially. So, if the solid retains or comes back to its position completely, then it is called perfectly elastic solid, or if it partially comes back to its original position, then it is called partially elastic solids. And the energy of deformation is stored as elastic energy in the solid, and then that energy is used for the solid to come back to its original position. So, the solids, they deform and then after some time they stop. So, the change or the deformation in the solid is non-dimensionally is termed as strain, whereas fluids, they deform continuously. So, a strain or a term strain which measures only the length or the dimension of deformation is not appropriate for fluids, because fluids deforms continuously. So, what is used there is the measure of deformation in fluids is rate of strain, which is a tensor, and it measures the rate of deformation of the material. So, you might have seen this image in many places. When a force or a stress is applied, then the fluid have a velocity, and that velocity profile is linear in case of Newtonian fluid. So, we will look at further what rheology is. So, the objective of rheology is that how does the fluid flow respond to the applied stresses or applied forces. As you know that stress is force per unit area. Okay. So, the objective of rheology is that how does the fluid stress is generally represented by the term tau. Okay, so we can write this tau is equal to F over A. Now the objective of rheology is to understand that how does a fluid respond to the applied forces. For simple fluids, for example, simple fluids can be water, gases, etc., which does not have large chain molecules or particles suspended in it. They are generally simple fluids. In such case, Newton's law of viscosity is followed by the fluid. So Newton's law of viscosity is a relationship between stress and strain. So tau is proportional to strain, and when then equality is brought into it, tau is equal to mu. This is not a strain, this is rate of strain. So the shear stress is proportional to rate of strain in case of a Newtonian fluid, and if we plot it on a graph, stress versus strain, you will get a linear relationship, and the slope is called viscosity. So the fluids which follow this simple relationship between stress and strain are called Newtonian fluids. Now one must remember that this is not coming from fundamental principle, but this is an empirical formula which has come from observation and measurement of stress and rate of strain in a number of fluids. So the relationship between shear stress and shear rate is linear in a Newtonian fluid, and the law is known as Newton's law of viscosity. Now what happens when the fluid is not simple? So all non-simple fluids can be put together under a term which is called complex fluids. So what can be complex fluids? Complex fluid, blood is an example of a complex fluid, because blood has number of particles suspended in it, and blood is further complex because the size of the particles, size of the molecules that are suspended in blood varies. It has long chain molecules such as proteins, anticoagulating agents, or the antibodies, antibodies, and number of things which are suspended into it in the plasma, plus particles, red blood cells, white blood cells, and platelets, which are of the size of few microns. So few nanometers to few microns, the size of the molecules suspended in the blood, and they affect the rheology or the rheological behavior of the blood significantly. So blood is a complex fluid. That is why we are studying this topic, rheology. Okay. Another example of complex fluids can be any suspension or any colloidal suspension. From chemical engineering perspective, all the polymers behave as complex fluids. Long chain polymer molecules are suspended in the liquid, so they are all non-Newtonian or complex fluids. So the fluids which do not behave or which do not follow Newton's law of viscosity are called non-Newtonian fluids, and most of these fluids are complex fluids. So the response of the fluid in such case is not simply linear, that is, it is not necessary that tau is proportional to rate of strain or the shear stress is not directly proportional to the strain rate. So in such cases, it is important to understand the rheological behavior or the develop a constitutive equation between stress and rate of strain, and that is the objective of rheology, and such equation which is obtained from rheology is called constitutive equation. And this can be done using experiments which has been done for last few centuries now, and now it is more and more also being done by molecular dynamic simulations, where people are modeling the behavior of molecules and then finding a constitutive relationship between stress, shear stress, and rate of strain. So the objective of rheology is to finally give a constitutive equation between applied stress and rate of deformation for complex fluids, because we know that for a simple fluid what is the law. So based on the behavior of these complex or non-Newtonian fluids, they can be divided into three different categories: time independent behavior, time dependent behavior, and viscoelastic behavior. Now this category or categorization is only for the understanding purpose, so we can demarcate different behaviors. It is rarely possible that a fluid, a complex fluid, shows only one type of behavior. It may be the fluid is showing all three kind of behavior, or it can show two different kind of behavior. So time dependent behavior means that the response of the fluid or rheological behavior of the fluid is independent of time, so it does not change with time. Some examples are shear thinning fluid. Okay, so the time dependent behavior can be shear thinning or shear thickening. Or another example, as I was telling, Bingham plastic fluids. So they show a non-linear kind of or non-Newtonian behavior, but that does not depend on time. The fluid does not have a memory, whereas time dependent fluid, the behavior is time dependent. It depends on the time, and the examples are thixotropic fluid and rheopactic fluids. So it may happen that the shear thinning behavior, a fluid showing a shear thinning behavior, but it is also time dependent. In addition to that, the fluids also show viscoelastic behavior. Complex fluid also show viscoelastic behavior, and blood is one example. So in this case, the fluid have viscous behavior plus elastic behavior. So as we discussed some time back, that the elastic behavior, that after the stress has been removed, the material regains its original position is elastic behavior. So partially the fluid regains its original position. Now this happens generally if the fluid is suspended with flexible particles. For example, blood has red blood cells which are flexible disc shaped particles, and those particles, when the shear stress is removed from them, they regain their shape. So because of that, the fluid also show viscoelastic behavior, some kind of elastic behavior. Okay, so we will look at time independent behavior in this lecture. One example is for first fluid that we will be looking at, Bingham plastic fluids. So Bingham plastic fluid, they still have the linear relationship between stress and rate of strain. So we can say that tau is equal to tau y plus mu gamma dot. So if we plot this on a stress versus rate of strain plot, then we will get this kind of behavior. This intercept is known as tau y or yield stress. So what does this mean physically? When we apply a stress on a fluid, one of the examples of this is toothpaste. So when we push the toothpaste, for some time the paste does not come out. Only after a certain or a critical amount of force, the paste starts coming out, and that is because when tau is less than tau y, there is no deformation. And when tau is greater than tau y, so as you can see on this graph that gamma dot is equal to 0 for tau is less than tau y. When shear stress is less than yield stress, then the deformation is 0, and when is greater than yield stress, then it follows a behavior like a Newtonian fluid. So if we plot a Newtonian fluid with the same viscosity, it will be a line parallel but passing through the origin, whereas in case of a Bingham fluid or Bingham plastic fluid, it will have certain amount of yield stress. And this is again a property that is shown by complex fluid which has particles suspended in it. So imagine a fluid which has number of particles which are which have taken a certain kind of shape in the fluid. They do not move until a certain amount of force is applied on them, and when the force increases, that critical force, or when the stress increases beyond that critical stress, they reorient themselves and the fluid behaves as a Bingham plastic fluid. So the Bingham plastic fluid, the property is that they show yield stress. Blood also shows an yield stress behavior, but not exactly Bingham plastic behavior. They have some non-linear relationship with it, which we will go. So again, let me emphasize here that the relationship between stress and strain again is a empirical relationship or a model, and in this case there are two parameters in the model, tau y, which is yield stress, and viscosity of the fluid, which is mu. Okay. For shear, another behavior is shear thinning fluid. So as you see here, they show non-linear relationship. So that means tau is not proportional to directly proportional to gamma naught, but it follows a power law where n is less than 1. So if we plot it on stress versus rate of strain curve, it will still go through origin, and this straight line represents a Newtonian fluid. The power law behavior will be, it is also known as pseudoplastic. So the slope of the curve in this case is less than what for Newtonian fluid. So the slope of curve will be, we can also say this is apparent viscosity, which will be defined as tau over gamma dot If we introduce a equality constant here, then tau will be equal to some m gamma dot to the power n, where m is called consistency index. So blood also behaves as shear thinning fluid under certain conditions, and there are a number of complex fluid which show shear thinning behavior. They have a power law kind of behavior, and n is less than 1, and its viscosity will be m gamma dot to the power n minus 1, and which is what this slope represent. Okay, sorry, the image shown here is for tomato ketchup, okay, which also behaves as a shear thinning fluid. Okay, for shear thickening fluid, as the name suggests, then when the shear is applied or when the shear rate increases, the viscosity of the fluid, when it decreases, then it is called shear thinning fluid. When the rate of shear increases and the viscosity increases, then it is called shear thickening fluid. So when the fluid thickens, because viscosity in general term or in general perception, viscosity represents that how difficult is it for a fluid to flow. So if it is difficult for the fluid to flow, then we will say that this fluid is thin. If it is difficult for the fluid to flow, then it is thick. If it is easy for the fluid to flow, then it is called thin fluid. So from that nomenclature, we can understand that shear thinning fluid, if the shear rate, when the shear rate is increased and if the viscosity of the fluid is decreased, then that means the fluid thins, then it is called shear thinning fluid or pseudoplastic fluid. Whereas when the shear is increased or the rate of shear is increased and the viscosity of the fluid increases, then it is called shear thickening fluid. They are also known as dilatant fluid. They again follow a power law kind of relationship. Tau is equal to m gamma dot to the power n, but n is greater than 1 now. Okay, so if we plot it as on a stress versus rate of strain curve, then this is for Newtonian fluid and this is for the shear thickening or dilatant fluid. One example is cornstarch and water solution. So if you dissolve or if you make a solution of cornstarch in water and you apply the shear is a low shear, or if you rotate it slowly, then you will see that it flows. But if you increase the rate of shear, if you rotate it fast, then the fluid does not move at all. So that is an example of shear thickening fluid. Another example of shear thickening fluids is quicksand. Okay, so combining two, we can give the power law model, and in the power law model, we can say again tau is equal to m gamma dot to the power n, where m is the consistency index and n is greater than 1, then and n is less than 1. So n is greater than 1, we call shear thickening fluids or shear thickening behavior shown by the fluid. N is less than 1, then it is called shear thinning fluid. However, in this model, what happens that if shear stress is very low, then the viscosity or apparent viscosity of the fluid, which is tau over gamma dot, that will be approaching infinity. That will be very high viscosity. Similarly, if shear rate is very high, then viscosity will be approaching 0, both of which are not correct representation of the behavior often. So some limiting behavior is to be applied, because this model, power law, which is given by Ostwald-Dewall, which is also known as Ostwald-Dewall model, it cannot describe the viscosity at very low and very high shear rates. So number of corrections to this behavior has been proposed, number of models has been proposed to correct this anomaly in the behavior of the power law model. One of the examples is Categorizing model, which is given by this formula. So you see there that eta is non-dimensionalized here. So eta minus eta infinity, where eta infinity viscosity, where eta is in this particular example, eta is viscosity, and eta infinity, eta at high shear rate, viscosity at high shear rate, and eta naught is equal to eta at low shear rate. So if you see, the left hand side is non-dimensional viscosity. On the numerator, you see the difference between the viscosity and the viscosity at high shear rate, and in the denominator you see difference in the viscosity at low and high shear rates. And this is equal to 1 plus lambda shear rate, lambda into shear rate to the power a, total to the power n minus 1 over a. So another new term here, which is lambda. So you see here lambda, you can easily identify, or you can easily see from dimensional analysis, that because shear rate has unit of time to the power minus 1, right? Because shear rate is what? Non-dimensional deformation per unit time. So non-dimensional deformation, no unit, and time second. So per unit time is second to the power minus 1, and lambda is a time constant, because when we multiply this to be non-dimensionless, dimensionless, then lambda is lambda will have a unit of time, and it is 1 over lambda is the critical shear rate at which viscosity starts to decrease. What is A? A, this power, it determines the transition between low shear rate and when the power law region starts. So if you look at, if shear rate is low, that means let us say if lambda gamma dot is very less than 1, then what will happen? Eta minus eta infinity divided by eta naught minus eta infinity is equal to 1, because this term will be negligible with respect to 1. So that means that eta is equal to eta naught, and it is Newtonian behavior with the viscosity of eta naught. Whereas at high shear rate, if lambda gamma dot is very larger than 1, then you can see that this term will go away, or 1 will go away, or you can neglect 1 with respect to this term, and this will give you eta minus eta infinity is equal to Okay, so this model shows at low shear rate Newtonian behavior as we saw here, and at high shear rate it shows power law behavior. So what we have done in power law model, we have combined the behavior. Power law model can represent or can show the behavior of a power law fluid. It may be shear thinning or shear thickening. In the time independent fluids, we have shown three kind of behavior. One is yield stress behavior, another one is shear thickening behavior, and the third one is shear thickening behavior. Now shear thickening and shear thinning behavior can be combined in power law model, and depending on that the power n is more than 1, then it is shear thinning behavior, and if the power n is greater than 1, then it is shear thickening behavior. If the power is less than 1, then it is shear thinning behavior. Now if we can have a model which can combine the yield stress and the non-linear behavior together, then we can model a fluid which shows power law behavior as well as yield stress behavior, and that can be done using Herschel-Berkeley law or Herschel-Berkeley model of for fluids. This is given as tau is equal to tau y plus m shear rate to the power n. So here we have combined the yield stress as well as power law behavior of the fluid. Okay, so that can be given as when n is equal to 1, when n is greater than 1, and when n is less than 1. Okay, so this model is known as Herschel-Berkeley fluid. So if a fluid is showing Bingham plastic behavior or and power law behavior, then its behavior can be given by Herschel-Berkeley model. Then another model which is very similar to Herschel-Berkeley's model, that means it combines the yield stress as well as power law behavior, is known as Casson fluid model. We look at it in general, what it can be shown, or it can be said that m is equal tau 1 to the power 1 over m is equal to, or we can give this another power, let us say tau to the power 1 over p is equal to tau y to the power 1 over p plus m gamma dot to the power 1 over p. Now if we say that p is equal to 1, that means we will get tau is equal to tau y plus m gamma dot, which is for Bingham plastic fluid. Whereas if p is equal to 2, then we will get root tau is equal to root tau y plus root of m gamma dot, and this fluid is known as Casson fluid, or this model is known as Casson model, and this often represents for the rheological behavior of blood. So in this, for blood, this p is equal to 2, and the fluid model is known as Casson fluid. Okay, as we said earlier at the start of this lecture, that blood is a suspension of different particles in fluid. So So it is important or it is useful to look at some of the literature that describes the rheology of suspensions or rheology of different particles suspended in a fluid. Okay. So blood is a suspension of different kind of particles in plasma, and if the volume fraction of these particles is small, as well as these particles are very small with respect to the length scale of the flow, that means the say if the flow is happening in a channel, in a artery, in a tube, and if the particles are very small with respect to the channel dimension, then we can assume it to be homogeneous fluid. So homogeneous flow means the viscosity is same in all the dimension, and the fluid as well as the particles move with the same velocity. Okay. And the viscosity of such suspensions will depend on a number of factors, which include the concentration or volume fraction of the particle. Let us say the volume fraction is given by phi. Shape of the particle, particles may be spherical, may be ellipsoidal, or it may be disc shape, which is the shape of RBCs, flexibility of the particles, and the mechanical properties of the particles. So if we take a simple case of spheres which are rigid, and the concentration of these spheres is very low, it is so low that we do not need to consider the interaction between the spheres, then for that Einstein has given a relationship for the viscosity of the spheres suspended, viscosity of the fluid which has low concentration of the sphere suspended in the fluid, and this viscosity is given as eta s, which is equal to eta naught. Eta naught is the viscosity of the fluid, and phi is volume fraction of particle. And this is valid for phi is less than 0.01. So if the concentration of particles is very small, then the viscosity of the particles can be given by this relationship, and as you can see from here that the viscosity of the suspension increases than the viscosity of the fluid. However, if the concentration of the particles is more than 0.01, and in such case particles interact, then the viscosity of the particles is further increased, which is given by eta is equal to eta naught plus 1 plus 2.55 plus 2.55 squared. You might notice that 6.25 is, this is just square of 2.55, and this relationship is valid for volume fraction up to 0.3. At higher volume fractions, the fluid starts behaving as a non-Newtonian fluid. Until volume fraction less than 0.3, phi is less than 0.3, the fluid behaves as a Newtonian fluid when the particles suspended is sufficiently small than the channel dimension. Now, if the particles are sphere but deformable spheres, for example droplets, because droplets will have a spherical shape, small droplets will have a spherical shape because of the surface tension, and if their concentration is low, so they show their behavior or their viscosity can be given by this formula. You might notice where eta d is the viscosity of the droplet. Okay. When eta d tends to infinity, that means the particles are rigid, then they will take, in case of eta d is infinity, then eta s will be is equal to eta naught into 1 plus 2.55. So they will come back to the relationship which we saw in the previous slides for rigid spheres. Okay. So in such case, when the spheres are deformable, the viscosity is less than that for the rigid particles, because the particles can respond to the stresses and they can reorient themselves. Now, if the particles are asymmetric, that means they are not symmetric in all the directions, which is say non-spherical particles, and for low concentrations their viscosity is given by eta naught 1 plus k phi. So this k is equal to 2.5 if it is symmetric particles, right? If it is sphere, then k is equal to 2.5, and this k will depend on different fluids. For different kind of particles it will have different number. In this case, what will happen? The particle will also rotate and they may occupy larger volume, so the viscosity of the particle will increase. But if the shear rate is high, then particles will tend to orient along the direction of the fluid and the viscosity will decrease, so they will show a shear thinning behavior. Okay. So at low concentrations you will see this kind of behavior, but at the same time this value of k will change when the shear rate is increased. So you can say that k is shear dependent. And the particles show shear thinning behavior for rigid asymmetric particles. If the particles are deformable and asymmetric, then the particles will rotate, they can change their shape so that the friction is minimized, and viscosity for such case will be lower than for rigid asymmetric particles. And because the particles can respond to the fluid, and if the shear rate is or if the shearing is removed, then they can regain their shape, so they will also show viscoelastic behavior. Okay. So for rigid or deformable asymmetric particles, but when the concentration is high, particles may form a continuous structure. They will show a yield stress behavior, so that when this structure is broken down, and this yield stress is a function of volume fraction. So blood has number of red blood cells, or the volume fraction of red blood cell is about 40 to 45%. So they show this kind of behavior which have deformable asymmetric particles. RBCs are asymmetric particles and they form a continuous structure, and a yield stress behavior is shown by them, and this yield stress will be a function of the volume fraction of RBCs. Okay. So in summary, in this lecture what we have looked at it is what is rheology, what does the term rheology mean, and what can be the different kind of behavior shown by fluids. We looked at time dependent or time independent behavior and viscoelastic. We categorized into 3 categories. At the same time we said that any fluid can show only 1 or 2 or 3 kind of behavior. Then we looked at some of the time independent behaviors, Bingham plastic, that means the fluid which show yield stress, shear thinning, where with the increase of the shear rate the viscosity of the fluid decreases, shear thickening, where with the introduction of high shear rate, introduction of the shear rate, the viscosity of the fluid increases. And we also looked at briefly the rheology of suspensions. We looked at different rheological models or different models for non-Newtonian fluids, and we said that for blood it shows yield stress, it also shows shear thinning behavior. And because it is suspension of particles and these particles are viscoelastic, so it also shows viscoelastic behavior. So it turns out that with all the components of the blood, the behavior of the blood changes. So it is important to understand that what does the blood constitute and the properties of those different particles. So in the next section we will look at the morphology of the blood briefly. Okay, thank you.